Okay, we're back. Now we're going to start with learning some ways to predict what partitions are going to produce for transmission loss or sound reduction. We'll begin with single leaf partitions. For examples, this could be concrete wall, sheet metal, something like that. The book gives 3 different conditions, and it starts with for normally incident plane waves. And we're going to be interested in field or diffuse, because we usually just don't have sound coming from one direction. We have it coming from lots of different directions. You might, in some case, have it coming from one direction. Say, from in the outdoor environment, you just have sound coming directly towards your building from some external industrial noise source, for example. But a lot of the time, it's going to be, say, from one room to another, you have diffuse sound field, you have reflections from all directions, and it's a different transmission loss for that. But these equations are, like we said, you might be calculating for specifically that, but then even when we do the diffuse field stuff, these equations are integrated into that. So I think I said that the book gives equations for 3 conditions. Those 3 different conditions are dependent on the natural frequency of the partition. So angular frequency, nod, that's the natural frequency. And as you should be familiar from vibrations, or I think we talk about this in measurements, there's probably a number of times where you have seen this equation throughout your engineering careers by now. The equation for that is the square root of the stiffness over the mass. So this is another difference between how we usually do things and how things would be done in Britain, but we have it like this usually. The book uses S instead of K for the stiffness. Same thing though. So the first condition is when it's for frequencies that are significantly less than the natural frequency. In that case, our sound reduction is going to be equal to 20 times log base 10 of the stiffness. Here we're defining the stiffness, and we're saying this primarily depends on this. All these, they're going to be heavily frequency dependent. So, but besides that, stiffness is driving it here. Like in some of the other ones, instead of stiffness, it's going to be mass. I just want to point out that frequency is always really important, either than stiffness or mass, depending on the situation. But then we also have in this negative 20 log 10, 4 times pi times the characteristic impedance. That's the density and speed of sound through the medium. So that's in there as well too. This one decreases with frequency by 6 decibels per octave. Typically, we are not concerned with this range. It is very low frequency, so this is usually going to be at frequencies lower than what we're looking at. Condition 1 and condition 2, it's good to know these equations, but we're probably not really ever going to be dealing with them. It's mostly just 3, but we'll cover them here quickly. So condition 2 is when we are at the natural frequency. In that case, all sound, so this, even though we probably aren't looking at this condition usually for a partition because it's such low frequency, it's still useful to realize this concept because there are going to be other resonances that we're going to study with other types of partitions here soon, where just understanding this concept of when we're at the frequency of that natural frequency or that resonance frequency, that the sound just passes through. It passes through unimpeded. We have no reduction of it. Now, finally, we have condition number 3, which is the one where primarily we're interested in. Here, the sound reduction is roughly equal to 20 times log 10, the mass and the frequency, minus 42 decibels. And there's this roughly equal to because there are other characteristics of the assembly that affect it that we're not accounting for here. But the mass and the frequency, they are the primary driving factors. There are more developed, more complicated equations to account for other things like stiffness, or when we get to the double leaf partitions to account for the resiliency between the two sides. But we'll just take this more introductory approach for now. This one increases with frequency by 6 decibels per octave. In theory, we'll talk about that a little more later. And this is what is known as the normal incidence mass law. So we're going to look at this for field incidence as well. And in that case, it's called the mass law. Just this is so heavily dependent on mass that it's called the mass law. So this last note here, I'm just pointing out again that this is for normal incidence, but often in the field we have waves that are incident from all directions, so we need to adjust this for that. This figure from the reading material lets us see it. So this is that condition we were just looking at. So when it's normal, the mass controls it. Then as we move away from normal, we have a region where the damping controls it, and then we have a region where the stiffness controls it. And we need to account for all these different regions in one equation. So this is just letting us know that this is for when we are at a frequency above the natural frequency. So here are the equations for field incidence and mass laws. And these are the ones that you would normally be using. They're in these big double red boxes to show that. We have one version here that's the, say, like the international version, where, so R is the symbol that we're calculating for. We're going to put in the mass in kilograms per meter squared. So this is a surface weight. Surface density. And then we have the frequency. In both cases, that's going to be in hertz. Basically, just the units of the mass and then the symbol used changes between the two of these. So down here, it's pounds per square foot. So these, like I said, these would be the main ones you'd be using. I did want to, but there are other factors that are determining how much sound isolation we're going to get, but those relatively simple equations don't account for it. Those equations are for mass-controlled limp barriers, which is an idealized condition. And this could be okay for something like mass-loaded vinyl barriers. That's what we're looking at here. So it's mass loaded, it's limp, it's made of vinyl. So these are usually a pound per square foot. You might have multiple sheets of them sandwiched together to get greater surface weights. But the main thing is that it's limp. And if you use something like this, then these equations apply. But if you use other common building materials, like say it's going to be the casing for something you're designing, you're using sheet metal, or if you're in an architectural situation and you're designing a wall made of gypsum board and has plywood in it, the stiffness of those is going to take it away from this ideal theoretical condition. And so this isn't in the book, but there is some people have done studies comparing this simple equation to common building materials like gypsum board. So if you are on something like that, say like an architectural situation, and you have these materials that are stiff, then this equation here has been adjusted to fit that empirical data better. And so I realize that giving you multiple equations for the same thing might be a little bit confusing for how you're supposed to solve problems. In this class, if you just stick with these, it's okay. If you want to instead use this, that's okay. It might be best if you did in your assumptions, put that in there. If there's like, if you're doing a problem and you know that this assembly has some stiffness, then maybe it's better to go to this one. But if you end up using that one from the book, you're not gonna lose a bunch of points. But it'd always be good to put some statement about that into your assumptions. Note with this one, you don't quite get the 6 decibels per doubling of frequency. It's more like 4 or 5. You have to do the math there, but just as a rule of thumb, it's more somewhere in that region. And this one does track pretty closely with empirical data. I'm gonna make another break in the video there so I don't lose all the work I'm doing and you have something for today's lecture.